Tectonic file system, efficiency from excess scale. Disclaimer, this video is for entertainment purposes only and is not created on behalf of Facebook and contains publicly accessible information only. Tectonic is Facebook's exabyte scale distributed file system. The purpose of Tectonic is for consolidating multiple large tenants that were formerly housed in different service-specific systems. The generalized file system aims to achieve similar performance as the former specialized systems, while enabling lower operational overhead, simpler services, and paved the way for better performance utilization. This talk is an overview of Facebook's fairly recently released paper, Facebook's Tectonic File System, Efficiency from Excess Scale. Please let me know in the comments below if you have any questions, concerns, or corrections about the contents of this video. So, what is it all about Tectonic? So it currently houses around 10 tenants. Prior to Tectonic, Facebook's storage infrastructure included a constellation of systems, including Haystack, which was one of them. Another example is F4. And another example includes their data warehouse infrastructure, which used HDFS, so Hadoop Distributed File System, which is an open source file system. Now, they have all of these different technologies, and then afterwards they all were migrated into Tectonic, which is a generalized file system. And Tectonic ultimately eases operational complexity because it is a single overarching system to operate. It's more resource efficient because it allows for efficient resource sharing amongst cluster tenants, which we will soon see. So for example, the Haystack system is a blob store, and it is a blob store specializing for newer blobs. So blobs are binary large objects, so for example, photos. So since those are for newer blobs, it's more likely that those will get queried. So for example, you may have a picture that you upload to your newsfeed on Facebook that's more likely to appear on other people's news feeds. On the other hand, we have F4, which may be for slightly older blobs. That's the purpose of F4. And in that case, F4 may not have as many requests, but there may be more blobs to store. So in that case, F4 would more likely bottleneck on disk capacity and not necessarily on IOPS, while Haystack is more likely to bottleneck on IOPS, but it may have spare disk capacity. So by having a generalized system, we may allow for more efficient resource sharing. So that's just a little hint into what this talk will be about. So in aggregate, there are 3 challenges that faced when Tectonic was being built. The first one is scaling to exabyte scale. Pre-existing solutions, many of them were not able to scale to the scale that Facebook was operating at, so they needed to create an in-house solution. This also includes being able to handle so many different tenants and also data sets for each specific tenant. The second one is also enabling tenant-specific optimization. We have different types of tenants, and different types of tenants may have different types of loads. For example, in a data warehouse, you may be more concerned about throughput. Meanwhile, in something like Haystack or F4, which are blob stores, you may be more concerned about low latency. An image may not be very large, but you may want to not have to wait 2 seconds for an image to load on Facebook. Meanwhile, for a data warehouse, it may be okay to have that lower latency at the beginning as long as you can sustain a throughput for large, for example, MapReduce jobs to be executed. And the third one is providing performance isolation across tenants. Now, providing performance isolation across tenants is very important because you may have, for example, a specific tenant that can hog all the resources, and then your other tenant that resides on the same storage fabric may run into SLA issues where they're not able to sustain their load. Your services may crash because, for example, using up all the memory or using up all the storage capacity. So in that case, you may not be able to effectively store multiple tenants on the same cluster. So there is a specific way that Tectonic solves this problem as well. So here are the high-level solutions for these 3 challenges. These are 3 high-level solutions, and we'll go in depth into each one. Now, for the first one, a high-level solution is disaggregating the file system metadata into independently scalable layers. So what does this mean? So we are disaggregating file system metadata into independently scalable layers. In essence, similar to Azure Data Lake Service, what it provides is the ability to spread out the metadata for where all these different files are stored in the storage nodes across several different nodes. So in HDFS, you may remember from my Google File System talk, the name node was responsible for storing the metadata, essentially concerning where all the different chunks are stored on which machine. You may horizontally scale out the storage of different files on different machines. We need to have some central location in order to create the mapping of indicating where those specific bytes are, on which server are the different chunks of data. Now, in a Hadoop distributed file system, that's stored on a single node, which is a clear issue in terms of scalability. On the other hand, Tectonic sort of alleviates this by disaggregating different elements of it, sort of peeling it off and distributing it across multiple nodes. And we'll see precisely how Tectonic achieves this. For the second one, for tenant-specific optimizations, this is achieved by using a rich client-driven microservices architecture. Now, essentially what this does is Tectonic allows clients to drive manipulation of data chunks instead of providing a fixed set of APIs within Tectonic itself. So for example, the blob storage uses a replicated quorum append protocol for reducing latency and small writes, and later read-Solomon encodes them. Meanwhile, for data warehouse, all writes are immediately read-Solomon encoded to improve network efficiency, reduce I/O consumption, and also reduce I/O space. So essentially, this is a client-driven microservices architecture. The advantage is that the client can specifically perform behavior that may be suited for that specific type of task, rather than Tectonic having to step in and provide all these by default and trying to mimic essentially what all the different tenants would enjoy to have. So the third one is performance isolation across tenants, achieved using a construct called traffic groups. So traffic groups is a construct created by Tectonic essentially to provide performance isolation across different tenants. This is a technique sort of used in their perfectly fair weighted scheduler. And essentially in traffic groups, they're aggregations of applications that fall under these groups, and later the umbrella groups are each assigned different classes as a proxy for their priority. So it's actually broken down into 3 different classes, bronze, silver, and gold, which we will see later. But in essence, traffic groups will contain these aggregations of different applications, and those will be used to provide restrictions in terms of resource management. So Tectonic has actually been in production at Facebook for several years, replacing the former Haystack F4 and HDFS systems. The impact of the transition facilitated large improvements, including a 10-time reduction in the number of warehouse clusters. It helped data warehouse handle traffic spikes with the spare blob storage I/O capacity, and as mentioned, it reduced operational overhead. Now let's go a little bit more in depth into Facebook's previous storage infrastructure. So, for the blob storage, blobs were typically immutable, and also they range from small photos, several kilobytes, to video chunks, which are in the megabytes. And again, we're optimizing for low latency. Haystack was the hot storage system. This one's for hot, and this one was for warm. So F4 experiences a lower request rate, so it actually uses read-Solomon encoding for improving space efficiency, though it has lower throughput. The overall issue with the 2 separated systems is that Haystack over-provisioned in storage while being able to accommodate more IOPS, while F4 lacked IOPS but had more storage. On the other hand, we had our data warehouse. This was the storage for analytics, including snapshots of the social graph tau, training for ML/AI models, and large-scale MapReduce jobs. The data is partitioned and used by different products such as ads, newsfeed, and search. So this one, again, like I mentioned earlier, has to be less latency focused, but rather focused on large throughput, larger writes and reads than blob storage. So as I mentioned earlier, one of the key problems was for the data warehouse specifically, they were unable to scale this effectively. And part of that reason is because in the architecture for Hadoop distributed file system, if you remember from the Google file system, we have something called a name node here. And then we have a series of different chunk servers here that are actually storing the different chunks. And the problem with this is that the name node is a single node here. And since this is a single node, we're not able to scale effectively. And it actually turned out that formerly large single datasets were often sufficiently big that they had to be split across several HDFS clusters. And through this, the compute engine logic became complicated as data had to be queried across clusters. Ultimately, this led to a two-dimensional bin packing problem. Where one dimension was handling the cluster's capacity constraints and also the available throughput per cluster. So we had to sort of optimize for the cluster's capacity constraints. And the other one is also the available throughput per cluster. So now let's take a look at the overall architecture and high-level design of Tectonic to more formally motivate this design. So as I mentioned earlier, Tectonic clusters are multi-tenant and support up to 10 tenants on the same storage fabric. It also supports any number of namespaces. So we support up to 10 tenants on the same storage fabric. Any number of namespaces and I also interact with Tectonic via an append-only API. It's a hierarchical. And although it's similar to HDFS, Tectonic's APIs are configurable at runtime, and this is what allows the tenants to match performance of specialized systems through this added flexibility. So if we want to take an overall look at the design, we can sort of draw it as follows. So at the very beginning, we have our client-driven architecture. So we're going to have a client library. And this will be the entry point for the different users. So client library is here. This is what communicates with the different chunks. And then on the other end, we have our metadata store over here. Now the metadata store is a little bit interesting because the metadata store isn't necessarily on a single node. So as I mentioned before, we have this disaggregation, right? So on one hand, we have the name layer. On another hand, we have the file layer. And on another hand, we have the block layer. Okay? And all of these communicate with a key value store, which we will talk about later, but this is spoiler. It's ZippyDB. Okay, so all of these talk to a key value store. Now also we need to store the actual chunks. So the way we store the actual chunks is the client library will communicate with the chunk store. And inside here, we have a fleet of different machines, all of them storing chunks. And so forth, and this is the chunk store. Last but certainly not least, we have one additional element, which I haven't really talked about, but it is the background services. So you can think of this such as anti-entropy repair. If you watch my my leaderless architecture video, but these are background services. So they're daemon processes that are stateless, And these include aspects such as rebalancing, garbage collectors, disk inventory, storage repair, and scan. So now we can go through each one individually and sort of see what their implementation was like. So the chunk store is a exabyte scale storage system. It's distributed in flat object store for chunks, which is the unit of storage in Tectonic. So in Tectonic, files are comprised of blocks, which are further stored in chunks. And there's actually two ways that chunk store contributes to exabyte scalability for Tectonic. So chunk. So there's two ways that the chunk store contributes to the scalability. The first one is the notion of chunks are oblivious to the higher level abstractions such as files or blocks. So this is all handled by the client library and the metadata store. Hence, it supports specialization of tenants' performance needs without having to pre-support custom file system management. And this is a large advantage. So essentially what this is that chunks are oblivious to higher So in this case, you can perform optimizations such as read-cell element encoding or deciding when to read-cell element encode, or if you want to use some sort of replication model as well. The second one worth mentioning is that the chunk store itself is flat, as the number of chunks grows linearly with the number of storage nodes. So we have that chunk store is flat. Okay. So how do these chunk stores actually work? So the underlying file system in each individual chunk node is XFS. This is the file system used on each one, which is a 64-bit journaling file system in Linux. And Tectonic uses a particular version which stores the metadata of the file system on the SSD, so append updates can happen more easily and quickly in the metadata. So each storage node has 36 HDDs, 36 hard drives, and a 1 terabyte solid state drive. So the 1 terabyte solid state drive can be used for both caching operations and also for storing file system metadata. In terms of durability, there are two main approaches. So for durability, we have first one is replication. So in replication, data chunks are copied into various domains, such as server racks. Background processes will repair lost and damaged chunks to maintain durability. Just to note that this entire thing is not actually geo-replicated. And that's actually an important consideration because clients will need to implement geo-replication on top of this system. And it is indeed implemented by various different systems. The second approach for durability is actually just read-cell element encoding it. So read-cell element encoding. So for a specific RS, R/K, the encoding block is split into R equal chunks and K parity bits. Okay. Now, this is the basic idea of how the chunk store works. The next major component is the metadata store, which is responsible for naming exabytes of data. So this is the metadata store. This component maps blocks to chunks. It also performs a disaggregation of different layers, namely the naming, file, and block layers. Scalability and load balancing will come naturally from this design, paving the way for exabyte scalability. So previously I mentioned these various factors that allow for exabyte scale in Tectonic. And here we'll see precisely how this all works out. So I'm going to draw a schematic precisely of the different layers used in the metadata store, and we will see how all of this fits in order to provide the scalability that we're looking for. So across the different components in the metadata, we want to be able to clearly identify where all the chunks are stored on which disk. So we're going to have different types of layers on one side. Everything will be stored as key values, so we have a key and a value. We will also shard the data because it will no longer be stored on a single name node like we saw in HDFS. And we will also store a mapping. So there's several different types of layers. The first one will be name. Then we will have file. And we'll also have block. Okay, so the name layer will have a key of the directory ID, followed by a subdirectory name. And it will also have a key of directory ID, followed by a file name. And the values that these map to are subdirectory info and subdirectory ID, followed by file info and file ID. So it may return a tuple, and this is sharded by the directory ID. Both. So essentially this creates a mapping of directory to list of subdirectories, but this is expanded, which we will see in a second what this actually means. Similarly for file, we may take a file ID and a block ID, and it may produce a block info, which is again sharded by the block info in this case. Whoops. And here we have a block mapping to a list of disks. And we also have a block which may have a block ID. Oops. To a list of disk IDs, sharded by block ID. And here we have block going to a list of disks, which are chunks. And I did a small mistake here. This one's actually from above, so this one is a file mapping to a list of blocks, which is expanded. And lastly, but not least, we take a disk ID, block ID, and then we create a chunk info. And here we have block ID. And here we have disk to list of blocks expanded. So several remarks I want to make. The sharded by is actually very critical in this case, because by sharding, first of all, we want to shard by either using something like a hash partitioner or using a range partitioner. ADLS, Azure Data Lake Service, they actually shard and use a range-based partitioning. And this is a little bit disadvantageous because it may lead to potential hotspots. Now, if we look at the name node, we notice that it's sharded by the directory ID. So this means if I do a lot of operations on the same directory, then they will most likely reside on the same shard. On the other hand though, if I also want to do something recursive on a whole folder, then when I go into a subdirectory, then it's less likely, or practically essentially, depending on the hash function, how many different shards there are, likely to become a hotspot. So within the same directory, since we're sharding, all the information will reside at that current depth in the same shard, but anything below it will not. And that is critical to this design because we're able to leverage any operation with the same shard consistency and linearizability. But on the other hand, we avoid hotspots because anything that resides on another shard won't be impacted and included in the same query. So that is one critical thing to notice. The other critical thing to notice is all of these expanded. And what this means by expanded is instead of storing a list, for example, of a key and a series of values, we instead simply store key value, key value, key value, spread out, and as the name suggests, expanded. And the advantage of this is that when you want to remove or add new values, you don't need to rewrite this list data structure. You can just simply append or remove, and this is more efficient because, for example, you may have an entire list and you want to remove something in the middle. It's a classic data structures problem. You may use a linked list, in which case you'd be removing an item, which may be somewhat performant, but then you have difficulty indexing it and so on. So using this technique, that sort of alleviates this problem. So this is the high-level approach of how the metadata store actually stores items. So for example, for the name node, if we have a directory ID, and we're looking for a subdirectory name, we just simply provide the name, and then we get the subdirectory info and subdirectory ID. Then if we want to get a file name, we have another operation for that. For files, we can retrieve the block ID. And then for blocks, specifically, we can retrieve information about which chunk it resides in. So all this information sort of aggregates down from these different layers: name, file, and block. And this is the guiding principle behind the metadata store. But all these different disaggregated, separately scalable layers that are sharded by specific keys provide a lot of benefits for the overall scalability of the Tectonic system as a whole. And now we can look more specifically at the actual key value storage. How is data actually stored? If we looked at our previous diagram from before, we noticed that we were using a key value store. So all storage is delegated to zippy db, which is a key value store created by Facebook that is fault tolerant, shared, sharded, and linearizable. Each individual shard stores an embedded SSD-based single-node key value store called RocksDB. So we essentially have a series of these RocksDB instances stored on each of those different shards. And the shards are furthermore replicated using Paxos, which ensures consensus across the different nodes. So while any replica can serve reads, strongly consistent reads must be performed through the primary node. So again, what this means is, since we sharded by these values, we sort of know where the master node and all residing components inside the directory at the top level live. So we may be able to leverage these strongly consistent reads. For multiple shards on a single instance, you may not have any cross-shard operations that are going to be atomic. Also, we create and populate multiple shards on a single node. The advantage of this is that if that node goes down, we may be able to, in parallel, recreate that node more easily, because then the remaining shards are located on separate different nodes. And that allows for a very parallel operation compared to having just one node acting as the entire replica of another node. Then it would put a lot of burden on that specific node to help bring back to life the node that just went down. Also, we have an optimization called sealing. Now, sealing for object metadata is an optimization that essentially creates and makes certain things read-only, so that way it can be cached more properly. The only thing to note is that we do not cache block-to-chunk mappings, as chunks can move across disks, hence invalidating block layer caches. So in terms of consistent metadata operations, we guarantee read after write consistency for data operations, move operations where source and destination are in the same folder. So how do we operate in cross-shard transactions? It's actually a non-atomic process. So for cross-shard transactions, we can look at this non-atomic process for moving a folder. As an example, moving a folder to a parent folder on another shard. So this is a non-atomic process. Here are the steps involved. First, we create a link from the new parent directory and then delete the link from the previous parent. So create a link from the new parent directory and delete the link from the previous parent. And 2, the move directory then keeps a back pointer to its parent directory, which is used to indicate pending moves. This indicates that only one move is active for a specific directory at once. So the move directory, then keeps a back pointer to its parent directory, which is used to detect pending moves. So this indicates that only one move is active for a specified directory at once. So there's actually issues that could arise with this whole setup. And one example is a race condition where a file named f1 in directory D is renamed to f2. And then we also create a new file with the same name at the same time. Since there's no cross-shard transactions, there is the possibility for multi-shard metadata operations coexisting on the same file to experience race conditions. These all must be done carefully. I'll provide an example right now for potential race conditions. So race conditions for cross-shard metadata. Okay, we have R1. This is the first example. We get file ID FID for F1. R2, we add F2 as an owner of FID. And R3, we create a mapping F2 to FID and delete F1 to FID in an atomic transaction. Similarly, we can create a new file ID FID new, and then we also map F1 to FID new and delete F1 to FID. So what actually happens here? We may experience a race condition if we do the following sequence: R1, C1, C2, R2, R3. In this specific condition, what will happen is that we'll actually leave the system in an inconsistent state. Let's actually sketch out precisely what happens. So R1 happens, we get for file F1, we will get a file ID of FID. However, afterwards we create a new file ID called FID new. Then we map F1 to FID new and delete this mapping. But then R2 adds F2 as the owner of FID. So it looks something like this. And then delete F1 to FID in the atomic transaction. But this no longer exists. This link is broken. So because of this specific race condition, the system can end up in an inconsistent state. And there's lots of different operations that may occur. So in this specific example, a new file named F1 in directory D is renamed to F2, but concurrently we are creating a new file with the same name. And then this is an example of a potential problem that may occur. Okay, so this is sort of the metadata store. Now we can continue on, talk about the client library. So client library. So the client library is specialized in orchestrating the chunk and metadata store services. So in our previous diagram, we saw that for the client library, the client library actually orchestrated calling the metadata store and the different chunk servers. The client library operates at a per chunk granularity, which provides flexibility in applying optimizations to run applications in the most optimal way possible. And the typical approaches for ensuring durability, as mentioned prior, include Reed-Solomon encoding or replication. There's also single writer semantics. Tectonic restricts single writer semantics per file, which avoids complexities arising from serializing writes from several writers. So this features single writer semantics, but per file. So the way this actually works is each file contains a write token. So this way is that upon every time a process opens a file for appending, a token is added to the file metadata, which subsequent writes must include. If another process then opens that file, a new token is generated, it's included in the metadata, and then only that specific process, because it holds the token, is able to write to it. For serialization guarantees, it is possible that you have multiple writers if the client library chooses to implement something like that. But the by default behavior is using this token-based system to ensure such semantics. So this is essentially all there is to the client library. Now on the other hand, we have our last component, which is background services. Background services aim, let's pick a different color now. Background services aim to maintain consistency across metadata layers, durability by repairing lost data, so that's similar to anti-entropy repair, and rebalancing data across storage nodes, publishing statistics about file system. So for this we have, for example, aiming to maintain consistency, durability by repairing lost data, and rebalancing across nodes. Okay. Also note that background services all process one shard at a time. So it's on a per shard basis. There's not really many operations that occur across multiple shards at once. Another example for this replication is the example of copysets. And copysets is mentioned in the paper. And the idea of copysets, which I found pretty interesting, is it's based off an idea found at Stanford in a paper that mentions how many times in distributed systems, it's very common for nodes obviously to fail. And if you have thousands of machines, failure will happen. It's inevitable. But sometimes you may choose a replication factor such as 2 or 3, and you don't really want to lose any specific data. If you do lose the data because one particular machine fails, then you will have to replicate it from another machine. But what happens if all the replicating machines fail? So if we have like 1,000 machines, we have like x1, x2, so on and so forth to like x1000, we choose a replication factor of 3, which means that any piece of data, for example, chunk, is stored on 3 different machines. We may say, okay, I get my data, I'm going to write it on one machine, and I'll pick 2 other machines at random to store my data. For example, x47, and then I replicate it on x68 and x421. Okay? So these are my nodes that are storing my replication with the replication factor of 3. Now, one of the problems is that if within my system I'm using a random selection for my different replicas, if I do happen to have 3 different failures of machines, it's almost guaranteed that I will lose data. And what this means is that it will cause a lot of headache operationally in order to find and restore that data from other logs or forms of cold storage. And it was found that oftentimes, in terms of engineering overhead, any lost chunks takes significantly more effort to find than potentially having it occur less often, even though more data is lost. And there's actually quotes by the HBase engineering team at Facebook mentioning how they specifically may choose this trade-off when it comes to losing significantly more data, but much less frequently, and very frequently losing small bits of data. But how can we actually balance this trade-off? The way we can balance this trade-off is that we can simply not use the random assignment when it comes to picking nodes. Instead, let's always pick sets of 3. And that's the idea of copy sets. The idea of copy sets is there's different sets of items of where we would choose to replicate. So here's an example. Let's say we always choose to replicate items in pairs of 3. So for example, if I write to x1, then I'll also write to x2 and x3. If I write to x4, I'll also write to x5 and x6. If I write to x7, I'll also write to x7, x8, and x9. So on and so forth. So we'll have some of these sets that are in sets of 3. Now, if I happen to have a failure on x47, x68, and x421, I'm most likely not going to lose any data at all. Because in order to lose data, I would need to lose data on, for example, x47, and then I would have to lose data on x48 and x49. Or if I were to lose data on x68, I may need to lose data on x67 and 69 as well. So this is just an example. Our total search space in terms of potentially losing data is much smaller, because now we need to have consecutive items, consecutive machines to lose their data, and not necessarily just any sporadic pair of 3. Now the disadvantage of this approach is that now when we do lose data, if x1, x2, and x3 fail, and suddenly we lost a whole lot of data, because a lot of data is focused on those 3 replication nodes. So this is sort of the trade-off that's done by Tectonic. It's about deciding when to focus on losing a lot of data at once or losing less data but more frequently. And another factor to consider is also how large are these copy sets. The larger the copy sets, the more storage is being used, but at the same time, we may have more reliability and durability. So these are the trade-offs that have been taken into account by the engineering team at Facebook when deciding how to incorporate this design. So this sort of goes through the high-level architecture and the main considerations taken when designing Tectonic. Now we can talk a little bit about multi-tenancy. So sharing resources effectively. As Tectonic handles a diverse set of tenants, it needs to have an approximately weighed, fair scheduler to ensure fair resource sharing and performance isolation amongst tenants. And there are 2 types of resources used in Tectonic: ephemeral and non-ephemeral. An example of ephemeral is disk space. And the reason why this is ephemeral is because it doesn't often change, at least in terms of capacity constraints. Oftentimes it is known, or the rate of growth is known. But an example of an ephemeral resource would be demands changing, such as IOPS. That could potentially change over time considerably. And because these things can be very dynamic, there may be certain optimizations, as we discussed prior, in order to fit multiple tenants and also maintain a fair solution so that all services can maintain their SLAs. So how do we distribute ephemeral resources? Ephemeral resources are managed at the granularity of groups, more specifically called traffic groups. And traffic groups reduce the cardinality of the resource sharing problem, which also reduces management overhead. Tectonic supports up to 50 traffic groups per cluster. And each traffic group is assigned a traffic class. The traffic class indicates the latency requirements and is used for deciding which traffic group is prioritized. Each tenant will get a predetermined quota of the cluster's ephemeral resources, along with each traffic group. So now that we have these different traffic classes and traffic groups, how does this actually work out? So we first have global resource sharing. So the client library would use a rate limiter in order to achieve the aforementioned elasticity. By using near real-time distributed counters, which internally, or as mentioned in other literature, is called operational data store, the demand for each tracked resource in the tenant will be measured in a small time window. The rate limiter algorithm is implemented using a leaky bucket algorithm. So we use near real-time distributed counters, and then perform rate limiting. leaky bucket algorithm. The throttling request at the client puts back pressure on clients prior to making a wasted request. But there's also local resource sharing. Local resource sharing includes rate limiters existing on metadata and storage nodes in order to prevent local hotspots. The nodes provide fair sharing and resource isolation using a weighted round-robin scheduler. It's a weighted round-robin scheduler. So the weighted round-robin scheduler provisionally skips turns of a traffic group if it would exceed the resources quota. It also needs to ensure that the collocation of lower latency blob store reads don't get collocated with larger reads such as from data warehouse. So for example, as we mentioned previously, there are different traffic classes. And traffic classes can be broken down into bronze, silver, and gold status. Gold status means that it is the most latency sensitive, while bronze status is not particularly sensitive, so it may be pushed back if a gold request comes through. So a traffic class request may miss latency targets if they're blocked below a lower priority request on storage nodes. And there's actually 3 optimizations for ensuring latency for gold class traffic nodes that happens in Tectonic. Let's go through the 3 optimizations. Of ensuring low latency for gold traffic nodes. 1. The weighted round-robin scheduler provides a greedy optimization such that a request from a lower traffic class will give up its turn for a higher traffic class if it has sufficient time to fulfill its request after the higher traffic class finishes. So if we have a higher traffic class such as a gold request, it takes a specific amount of time, and we have a bronze request coming in, we may push forward to have the gold request happen before the bronze request, as long as this is the acceptable window for bronze. So essentially we push back bronze in this direction because this still finishes before and we have this much buffer room anyway. This is in contrast to if we just did bronze earlier and gold here. This is bad because we want to optimize for the gold request, which is more latency sensitive, to occur before the bronze. So this is a fairly straightforward optimization. The second one is the disk may rearrange I/O traffic requests, such as service a non-gold prior to gold. So for this, Tectonic will stop scheduling non-gold requests to disks should there be a gold request pending on the disk for a threshold amount of time. So for this example, let's consider there is a series of different I/O requests, including one gold request as part of the I/O requests here. We may find that the disk may rearrange I/O traffic requests to service a non-gold prior to gold. So if we are about to service non-gold prior to gold, Tectonic will actually stop scheduling non-gold requests to disk should there be a gold request pending on the disk for a threshold amount of time. So T is greater than or equal to threshold. It may not service non-gold requests for the time being, and gold gets fast-tracked to the beginning. Also, if there are conditions, so for the third optimization, if there are pending gold requests here, then in order for the actual machine to service the requests, any request that is non-gold may be rejected immediately, and that will provide back pressure onto the client. So that is the third and final optimization that's used for gold traffic nodes. So as with any multi-tenancy here, we essentially shown that for ephemeral types of resources, we create a fair sharing process where we divide different applications into traffic groups, which minimizes the cardinality and management overhead. And for each of those traffic groups, we apply a traffic class. And based off of the traffic class, we have certain rules that will allow gold or latency sensitive traffic groups in order to skip the line in the weighted round robin scheduler in order to be processed earlier than other types of requests. But as with multi-tenancy, we have another topic worth discussing, which is access control. So Tectonic uses a token-based authorization mechanism. This may remind some of the single writer semantics from the client library. A dedicated authorization service would authorize top-level client requests, such as opening a file, by generating an authorization token for the next layer used in the system, and this process continues down the different layers. So we discussed over here the different types of layers in the metadata store. As we go through down, we may receive different types of tokens in order to provide access. The tokens payload will describe the resource given access to, which allows granular access at each layer. The verification process itself happens in memory, which is efficient and can be processed in the order of tens of milliseconds. There can also be token passing to reduce the access control overhead, such as avoiding repeatedly calling the authorization service. So in our original diagram, we may actually need to augment this authorization service to have a clear picture. So the overall grand scheme of things, it uses a token-based authorization mechanism, and also it uses this dedicated authorization service which authorizes top-level client requests at each layer of the different services, which is also unique. So this does it on a per layer basis. Okay. So this is the basic ideas behind multi-tenancy, which is one of the various challenges that Tectonic was facing. And for the other one is also the ability to have tenant-specific optimizations, which is the next component worth mentioning. So this was the third challenge, the tenant-specific optimizations. So there are two optimizations that pave way for tenant-specific optimizations that sort of distinguishes Tectonic from other systems. The first one is that clients enforce configuration on a per call basis. Unlike HDFS, which configures durability on each individual block write, the metadata store, as it's more scalable, facilitates operating this on a per block basis. The main advantage of this is that you may have different cases where you want to ensure different configurations. Because the metadata store is significantly more scalable in Tectonic compared to HDFS, this will allow the system to have such optimizations. And the second one is that tenants have nearly full control over how to configure an application's interaction with Tectonics, which includes chunk level granularity. So for example, the optimization for iris encoding lazily for blob storage. So tenants have full control over how to configure an application's interaction with Tectonic. So several specific optimizations that we see deployed by tenants include, first of all, hedged quorum rights. So this was released by a paper from Jeff Dean for resolving tail latency loads from querying multiple replicas. So Tectonic uses a variant of quorum writing for reducing tail latency without additional I/O. So one of the ideas behind the hedged quorum rights is that when you're performing any request, you may be performing it to several replicas, aiming to reach some sort of quorum. But some of those replicas may take a longer amount of time to reply to. It may be down or may be unavailable or overloaded. Instead of sending it specifically to the amount of nodes that you need to fulfill the request, what about sending it to more replicas and asking for their availability ahead of time? This is sort of known as the hedged quorum writes. So Tectonic uses a variant of quorum writes without asking for additional I/O. And the way this is achieved is that rather than sending chunk write payloads to extra nodes, Tectonic sends reservation requests ahead of the data and then writes to the first nodes that send the reservation. So you may have Tectonic here, and you have requests, so this would be the client library, and it sends it to a bunch of different nodes, reservation, and you only really need 3 of them to send requests back. And these are fine if they don't reply. We got 3, which is good. Now, here's another example. So if we rs encode 9 and 6, the client library sends requests and reservation requests to 19 nodes with reservation requests. Versus regular 15. So we may have slightly more network overhead, but this is very marginal. We do not incur an I/O penalty because this is just simply a reservation request. So this is a slight variant on the actual model used and mentioned by Jeff Dean. For the first 15 that accept, we send the write, and then we wait until at least 14 reply that it is a quorum. If the 15th write fails, we depend on the entropy background process to fix it. So what this means is, first of all, we send 19 reservations, and we don't even wait for 15 approvals. We can accept it with just 14. Afterwards, we pick a threshold, and then for the remaining, we depend on the entropy background process to fix it. So using hedged quorum writes, we achieved a roughly 20% performance improvement. At P99. And this is very important because you want to ensure certain latency considerations, and at P99, that's often where we start seeing issues where certain nodes may be unavailable, so this alleviates this problem. The second example would be the blob storage optimization. So for blob storage optimization, Facebook stores tens of trillions of blobs, hence the quantity of blobs needed to be indexed is a challenge in and of itself. We may have all of these different sort of files lingering around, and even just using the metadata store, storing trillions is quite a big challenge. But you'll notice that the files tend to be small, so Tectonic in turn tackles this problem by storing multiple blobs together in log structured files, such that new blobs are appended to the end of the file. To locate blobs, they are indexed by blob ID to the location in the blob found in the file. They are written as partial block appends, such as to be read after write consistent. However, they are replicated, hence they use more disk space. So what this actually means is that we may have a specific file that stores an index inside the file indicating what the different offsets are. So in order to locate blobs, they're indexed by blob ID to the location in the blob found in the file. So here we may see this blob XY is at offset 20, and then XZ is at offset 21, so on. And then inside here, we can look at 20 and 21 to actually identify the blob. So the advantage of this is that we incur a little bit less overhead in terms of actually locating the file that contains all the different blobs, because we may have a set restriction on what the size of the different chunks are and so on. So in order to compress them all into one file, we receive an optimization in this form. Okay, this is one approach. So these are sort of the approaches for tenant-specific optimizations that are used in Tectonic. Now another thing we can talk about is production trade-offs that are used in the system. So some production trade-offs, it's not all just fine, because an issue that may occur is that there may be higher metadata latency. HDFS metadata operations are in memory and are all stored on a single node, but we introduced scale by scaling it out and sharding the data. For Tectonic, they're stored in disaggregated metadata layers in a sharded key value store. This means that Tectonic file operations may require greater than one network call. For example, open would interact with name and file layers. So this means that the data warehouse had to adjust handling of several operations due to additional metadata latency. So we have increased metadata latency because of this aggregation / layering of metadata plus sharding on different nodes, and this caused an issue for data warehouse. Another issue is actually the approach of hash partitioning. This is one, so this is a latency. The next one is hash partitioning. Since Tectonic directories are hash partitioned, directory list operations can now work as subdirectories do not reside on the same metadata shard. So this means that listing directories may require recursively involving querying many shards. So performing So unlike HDFS, Tectonic does not have a disk utilization. So Tectonic DU, and instead periodically aggregates per directory statistics on usage, which may be stale. So this is part of the background services that run. So this is an issue with hash partitioning. And recall that we use hash partitioning specifically because we wanted to avoid those hotspots in the metadata. So something like Azure ADLS, Azure Data Lake Service, does not run into these issues because it uses range partitioning. So we may have subdirectories coinciding within the same range. Lastly, another thing worth mentioning is that several services do not use Tectonic. This is because they are, for example, bootstrapping services such as Configurator, and other systems may, using the underlying systems, leverage Tectonic, such as different services using Blob Store, may not be directly using or residing in Tectonic. Yeah, so this is an overview of Tectonic itself. Several other related works that are worth mentioning include HDFS and GFS, so Hadoop Distributed File System and Google File System. These ones are designs that use single node architecture for metadata. Another one worth mentioning is federated namespaces for increased capacity. So for example, Azure Data Storage or Windows Azure Storage. So this is Windows Azure Storage for federated namespaces. Another example of disaggregated and sharded metadata includes the Azure Data Lake Service and HopsFS, which increases file system capacity via disaggregation of metadata into layers on separately sharded data stores. But again, ADLS and HopsFS, they also use this disaggregation of file system metadata, but they use range partitioning. And on the other hand, last but certainly not least, Colossus is another system. So Colossus is another system by Google that provides cluster-wide multi-exabyte storage that is also client-driven. So this is an example of a client-driven design. But instead it uses Spanner, which is a globally consistent database for file system metadata and not systemdb, not zippydb. So zippydb only provides within shard strong consistency and no cross-shard operations. However, this specific limitation hasn't really been an issue at Facebook itself. So yeah, these are the related works if you're interested in checking them out. HDFS, GFS, Windows Azure Storage, Azure Data Lake Service, HopFS, or Colossus. Hope you enjoyed this quick talk. If you have any questions, please leave them down below, or if you have any feedback. And thank you very much for watching.